Hi everyone, Mr. Hamilton here. We're going to pick this video up where it left off with the Khan Academy video, giving us this equation right here. And we're going to take it a few steps further. The first thing I want to do with that equation is I want to rearrange it to get sine theta by itself. Now I've put a little m here because the angle, and you can see here I've got two different angles labeled. The angle is dependent on which of the m values we're talking about. If we're talking about m equals 1, we're right here. If we're talking about m equals 2, we're right here. And so the angles are going to be different, obviously. So taking this a couple of steps further, we often see that the length from the single slit to the screen is much bigger than the length between the destructive interference points. And we can see that in the video link below that I've put. There's a professor that does a single slit interference, and he literally has to shine it across a very large room just to get a very, very small interference pattern that you can see only when you're close up to it. So in regards to that, the interference pattern was the y1, y2, and so in general we're saying here that L is much larger than any y, whether it's y1, whether it's y2, whether it's y3. The distance from the central max to any minimum. That's what I'm referring to here. The distance from the central max to any minimum. Right? Minimum are the destructive interference points where we have the dark spots. The maximum are where we're going to see those bright spots. All right, so if that length from the slit to the screen is much larger, then what that means is that sine of theta m, which I have up above, is equal to m lambda over w. Then that is going to become tan of the angle, which is going to be equal to m lambda over w. Now this is an approximation that we're making because, as we said, anytime the distance to the screen versus the distance of the pattern appearing on the screen is very different, sine theta is approximately equal to tan theta. That's a generalization we made in our last video, and we're using that again. That only applies when we have very small angles, as we do here. This is a very, very small angle, much less than 1, so we can make this approximation. So let's continue that approximation. And we're going to say here that because tan theta, and I guess we should say tan theta m, tan theta is equal to ym. If we go back to our diagram here, tan theta is equal to the opposite over the adjacent, which is L. So it's equal to y1 over L or y2 over L. It's equal to ym over L. So that's approximately equal to, you can write it like that, or you can write it with two squiggle signs. It doesn't really matter. But we get this. And then it's just a matter of rearranging this equation. So we get ym is approximately equal to m lambda over w. I should add an L here as well, because it's m times wavelength times the length, that's separation between the slit and the screen, divided by w. And this applies specifically to destructive interference. So ym is the distance to the dark fringe from the middle of the central bright fringe. L is the distance from the slit to the screen. M is the fringe order number, which can be positive if we're going up, negative if we're going down. We could put that in terms of a different thing if we want. In a question, we could say down is positive or negative is up, but that would be specifically in that question. Otherwise, we'll just assume positive is up. And then W is the width of the slit. We can rearrange this a little bit for constructive interference. If we do that, now we're putting an approximately equal to sign, but really it's often just an equal sign because the approximations are so good. In terms of constructive interference, we have to add a half of a wavelength here. And so by adding m plus a half, we get the following. And so what we're finding here is this is going to give us our distance, ym, to each successive bright fringe. So y1 in this second equation's case would be the distance to here. So from that central, I'm just going to go up a little bit so you can see this. From here to here, that's the y1 in the constructive interference case. In the next one, we'd have y2. That's the distance to this right here, that other constructive interference case. And so that's how we're able to find the constructive interference. Now, if you have the McGraw-Hill-Ryerson Physics 12 textbook in front of you right now, shouldn't be any problem for having a look at page 401. They walk you through this example really well and just give you a practical way to calculate this. It's very similar to the calculations we've done for Young's double slit experiment. And so questions you're working on are on the next page, on page 402. And again, as always, if you have any questions, feel free to contact me. Thanks so much.